In this video, I'm going to discuss the principles that must guide the design of a physiological model. Also, I'm going to show how to interrogate a model to make inferences or draw predictions about the behavior of a physiological process. So we will demonstrate the principles of model design using an example. As I said before, I intend to adopt the project-based learning in this course. I believe that the best way to learn modeling, processing, and methodology is through examining specific physiological models. We call it case studies here, and working on hands-on projects using computer programming. So let's assume that we must design a model of a bioreactor. So bioreactor is also called chemostat. So chemostat is the graph here shows the growth the chemostat, or we call it a bioreactor. So bioreactor is a continuous stirred tank reactor used for production of microbial biomass. So it's a chamber used for producing microbial mass, such as bacteria. It consists of a freshwater and nutrient reservoir connected to a growth chamber, or also we call it reactor, filled with microorganisms. Okay, the mixture of freshwater and nutrients is pumped continuously from the reservoir to the reactor chamber and providing feed to the microorganisms. And the mixture of the culture and fluid in the growth chamber is continuously pumped out and collected. So it's called effluent here. Okay, so note that the in and out rate of the medium flow are kept constant for both in and out. And also they are regulated so that the culture volume inside the chamber is kept constant. So the model, this model here, is a bacterial growth model. He described in this module is actually linked to the cancer growth model we will discuss in the next module. So this is served as a foundation or a prerequisite sort of knowledge for the next module 3, when we model the cancer growth. So in this chamber, the fluids and bacteria are continuously stirred so that we can assume that the distribution of the microbial mass or bacteria within the chamber is both uniform and steady. Okay, so the constraints considered so far, such as the constant supply of nutrients, therefore the constant influx rate, and constant output flow rate, what we call the effluence rate, the uniform distribution of mass, the continuous stirring, meets the physical usage of bioreactors in pharmaceutical and manufacturing industries. For example, in pharmaceutical industry, the production of insulin, the insulin for diabetic treatment. So the question here we're using model to answer is how to adjust the effluence rate. That is the rate of pumping out the mixture for maximum production. Okay, so what do I mean here is in order to collect the microbial mass or bacteria efficiently, the effluence rate should not be too small. Otherwise, there's a detrimental sort of accumulation of bacteria inside the chamber that is not drawn out fast enough. Of course, this effluence rate cannot be too large. If it's too large, then the bacteria in the growth chamber may wash out. So in order to determine the optimal rate of pumping out the mixture, we need to develop a mathematical model. So provided now we know what to model, we want to model. So this is their variables we need to sort of calculate, which is the density of bacteria. So we want to model because we want to model the growth of bacteria inside a bioreactor. So our first step consists of identifying the variables whose evolution will be captured by this model. So in this problem, we are interested in the density of bacteria, which is the mass per unit volume. So this should be surprised because the growth of bacteria is the purpose of the bioreactor. And therefore, by tracking the density of bacteria, we can assess the growth process of the bacteria. So the second step consists of identifying constraints or assumptions that may affect our model, specifically the biophysical relationship that holds between different variables. So in this problem, it is fair to assume that because the nutrients and water are provided as a constant rate, so the growth of bacteria happens at a constant rate as well. This means that that variation of the density x over a finite time delta t should be proportional to x according to a rate parameter we call R here. Okay, so this R indicate the constant proportionality, okay, proportionality between the growth of the bacteria and the density of the bacteria. The growth means the change of their density. Okay, the change of density over time should be proportional to the density of the bacteria. So as you can see, if delta t goes to 0, what happened is this is actually, if we move delta t to the left side of the equation, okay, that becomes a derivative. Okay. So then we can we can use this constraint to derive a differential equation describing the evolution of the density x. In fact, as delta t, you can see as delta t converging to 0, this relationship results into an ODE, ordinary differential equation here. However, we should be careful here because we have so far established a constraint or assumption that the growth of bacteria happens at a constant rate. Okay, from this hypothesis, we can draw the physical relationship that forms a differential equation. In other words, is the model of our process. However, when we solve this differential equation, it should be very easy to solve. You can see the solution of this becomes using separation variable. I don't think it's integration by parts. It's just separation of variable. And then we can get this exponential growth, sort of analytical solution. Okay. So if we limit ourselves to this differential equation as growth model, so the solution xt would be exponential, it's exponential function. And then it will be unbounded. I mean, it's going to go to infinite. Okay, it's grow exponentially, getting larger and larger and faster. This clearly cannot happen because I cannot stack more than a certain number of bacteria in a unit volume. This means that the density x will reach certain saturation. Okay, so it cannot grow indefinitely. Also, the chamber has a finite volume, and therefore I cannot host more than a certain amount of the microbial mass or bacteria at any time. So this highlights important facts that the modern modeling process. Our equations depends on the constraints and assumptions that are given. If we do not gather all the constraints and assumptions, our model will suffer. So what is the issue here? Well, the issue here is that, sure, we lay down one constraint regarding the growth of the bacteria. However, we have clearly forgotten something. So we have forgotten that there's a limit to the amount of the microbial mass or bacteria that can be hosted in a unit volume. And therefore, there is actually a maximum of density of bacteria. Beyond this maximum value, the bacteria just cannot go beyond this maximum density. So we should stop here because the chamber is bonded and the density of bacteria cannot grow exponentially forever. So now we identified there's another constraint here is there's a maximum density B, we call it B here, that the density of the bacteria must reach, okay, must locked at that maximum density, cannot go beyond that maximum value because the bacteria is bonded inside the chamber. So I can incorporate these constraints into my model by changing the rate equation as shown here. Okay, so we add this additional term here. So what this additional term means, so this additional multiplicative term is 1 minus x over b is meant to assure that x does not exceed b. Because in fact, when x equals to b, then the derivative will be 0. If x equal to b, so x over b is 1. So 1 minus 1 is 0. So then this derivative will be 0. That means the x will stay constant at the maximum density value b. Because when x equals to b, the dx dt equal to 0 means the density of the bacteria will stay at that level, will saturate or locked at that level. So by solving this equation with this additional term, okay, so we get xt as a modified exponential growing function that is saturate or logs at maximum density b. So we can use integration by parts, and we can get the solution. So this is an analytical solution. As you can see, this analytical solution, x is actually when t goes to infinite, so this term here will become 0, and then x when t goes infinite will equals to b. That means the density of the bacteria will sort of saturate or logs at the maximum density b. So you can see how the process has been moving along. One constraint with a physical relationship, we get a differential equation. By adding another constraint, I'm able to modify the ODE by incorporating additional terms to accommodate this new constraint. So shall we stop here? Okay, so this actually still does not look quite right either. So well, think about this. Even though the density now saturates, the volume of the chamber is finite. So the influx of water and nutrients is constant. Okay, so what we're missing here? Oh, there's outflux. So we did not actually consider outflow. In order to keep the volume of the reactor constant, as the nutrients get in, we also have to have a steady outlet of bacteria, or extract the bacteria out of the tank or out of the reactor. Okay, so in order to keep the volume in the culture volume constant inside the reactor. So that's called S to be the rate of extraction rate of the biomass. Okay, that's called S. So we identify a new constraint, which is the microbial biomass is extracted at a fixed rate S in order to keep the volume inside the chamber constant. So I can factor in the extraction rate in my model as reported here, where the term in the red capture the constant efflux of bacteria. So I hope you appreciate the modular nature of the modeling process here. So we have started with one ODE that come from, say, biology or physiology. As we have more and more constraints, we have expanded the terms in ODE. We have add this term, and now we add this term here to accommodate new constraints and assumptions as they come. So let's say this is the final model for now. So what should we check? Okay, of course we can, just solve this by, either analytically by solving the differential equation or numerically using ODE solver in MATLAB. So, but before we you sort of like jump into solving the equation, getting the analytical or numerical solutions of xt, we can calculate very easily. We call equilibrium points of the model. So what is equilibrium point? Equilibrium is a value of, in this case, x, for which dx dt in the model is 0. Is the left-hand side dx dt is 0. That means it reached, we call it equilibrium, also called steady state in the future module. Is there, once they reach this equilibrium, then it will stay at that value indefinitely. Okay, because the derivative of it in terms of t is 0, means it doesn't change over time anymore. Okay, hence it's important to understand what the points of equilibrium are. In other words, which value of x, which value x can settle, okay, on the long run. Means after a very long time it settle, not a very long time. After a while, it will settle at equilibrium and will stay there. Okay, to calculate the equilibrium point, we can set the left-hand side, or we can set the derivative to be 0, which is left-hand side to be 0. That means right-hand side is also 0. Then we get a, based on right-hand side is a polynomial equation in x. So we can just find the zeros of the polynomial. So in this case, it's very easy. If we assume this equal to 0, we can solve the polynomial. We get two. If we solve this to be 0, we get two actually solutions for this, because this is a quadratic equation. We get two solutions for this. One is x1 equal to 0. Another one is x2 equal to this. Okay. So the first equilibrium, x1 equal to 0, it's kind of trivial. What is x1 equal to 0? That means if there's no microbial mass in the chamber to start with, if there's no microbial mass to start with, then nothing will grow from it. Okay, so this is a fair consumption, but it's trivial, so it's not very useful. It means if there's nothing to start with, then there's nothing will grow out of it. So let's look at the second equilibrium point, so x2. So for x2, you can see there is a if or, which is the production rate or growth rate of the bacterial, is bigger than S, which is extraction rate or efflux rate, then X2 is positive. Therefore, we can expect that bioreactor can settle at a steady state production of biomass or bacterial with constant density at X2. Okay. If vice versa, if R smaller than S, so what X2 means, what is X2? X2 will become negative. Okay, you cannot have a negative density, right? So the density of bacteria cannot go negative. So this is impossible. So because we cannot have because of definition of density, it has to be above 0 or something bigger than 0. Hence, we can conclude that this equilibrium, when R smaller than S, is not biologically reachable, NBL, not biologically reachable, and shall therefore be ignored. So now we examine sort of the equilibrium point. Okay, now we can solve the differential equation. So this differential equation can be solved analytically. So this is by using the integration by part, we can get a solution here. Okay, we can get a solution here. Can we have a exponentially growing function which reaches a saturation value as t increases? Okay, when t equals to infinite, that is the saturation level. So you can see when t equals to infinite, so this term equals to 0, then what is the saturation? You can easily solve it. It actually is equal to the x2 in the equilibrium point that we just solved in the last slides. So you can see that the saturation value is no longer b. It is instead a value lower than b. Okay, which is actually x2, which is x2 here. Is a value here you can see is lower than b. This is the one. Imagine t is going to infinite after a very long time. It reaches steady state. So this term is 0. So then the term, the xt, become this x2 actually in the last slides. You can see this is the value because uh, S is smaller than R. So this is actually a value that is smaller than B. Okay, it's not B anymore. Okay. So this value, this new saturation value depends on the balance between the rate R, which is the production rate of the bacterial, and the rate S, which is the removal rate of bacteria from the chamber. So the asymptotic value of saturation is reported here. Okay, reported in this value here. And you can see here, this asymptotic value is just equilibrium value x2 in the last slides. Okay, so this expression is basically telling us that we will never reach maximum density B because of the steady removal of the biomass from the chamber. So this steady removal of biomass from the chamber makes it impossible for the bacteria to proliferate to the maximum extent possible. However, it will reach a lower maximum density, which is given by the equilibrium x2, which is this value here, which is a value less than b. Okay. So now we have a model. We know that this model tells us the density x will reach equilibrium, and that such equilibrium depends on the balance between the rate of growth or production of bacteria R and the rate of the removal of bacteria S in the chamber. So how can we use this model for a design purpose, which is to answer the question I raised earlier? So what rate S should be chosen to get the largest harvesting amount of bacteria? Okay. So that is how that is to say, how should we regulate the efflux rate S to achieve the largest harvesting of bacteria? Okay. Asymptotically, meaning at steady state. Okay. Notice that the largest harvest rate is not X. Okay, it's not the largest density. Okay, it's actually the largest harvest rate, the largest harvesting amount of bacteria. It is actually X times S. So the amount of bacteria that is extracted is the product of X, the density of bacteria, and the S, the efflux rate. So we want to maximize the S times X at steady state. Means at steady state. Means we want to maximize this output S times X times S. Okay, asymptotically. Asymptotically. Okay, that means when we reach steady state, we want this output X at steady state or at equilibrium, which is X2, which X2 times S. We want that to be maximized. So that means we know that xt, okay, at steady state at the equilibrium point is x2, which is this value here. So the output, as I say, show here, the output is x2 times s. So you can see the out here is s times x2 times s2. Okay, so we want to maximize this. So we want to maximize this. So how to maximize this? Okay, how to maximize this? So it's basically, if we want to maximize this, what is this? Is we want to maximize this. S is, in this case, S is the variable. Okay, S is the variable here. So we want, you can see this is actually a quadratic function. You can draw the quadratic function, and you will see it's actually a concave function of S. Okay, there's a concave function of S, and then you can see that there's two roots. The two roots, S equal to 0 and S equal to R. Okay, and then this concave function will reach the maximum at when S and when S, so the two roots is 0 and R. So the maximum is actually in the middle, which is R over 2, which is also, you can think about, since the amount of extracted biomass is a concave function of S, the maximum will be reached when the derivative of out here in terms of S is 0. Okay, so it's 0. When derivative is 0, it means the slope is 0. Okay, that means it reached a maximum point. And we can solve this easily. Okay, d out over ds equal to 0. Then S, we call x a star here. That means they're at steady state. When S equals to R over 2, not at the steady state. When S equals to, if we choose S to be R over 2, that means we will reach the maximum harvesting of bacteria. So what's the conclusion here? Okay, so this means the bioreactor operates most efficiently. Means what is most efficiently means the reach the largest harvesting of bacteria when S equals to R over 2. So S is the efflux rate, and R is the growth rate of the bacteria or production rate of bacteria. So when S equal to half the growth rate of bacteria, then the model will the bioreactor will reach the largest harvest rate. Okay, largest harvest rate at steady state means it will, you can keep this going forever. Okay. So no more, because if you have bigger, if S is bigger than R over 2, then that will deplete the chamber. So you basically extract the bacteria too fast. Okay, you would deplete the chamber. So no less, because that will cause a detrimental accumulation of bacteria in the chamber that is not drawn fast enough. Okay, with that, I conclude the sort of the mass part of the of this model, of this bioreactor model, and so we can make some conclusions in terms of how this can inform us to build and to analyze the physiological models. So a paradigm for physiological modeling is this: first, to identify the variables to be modeled. Okay, so we basically translate from sort of like a physiological term into a mathematical, basically translate the physical or physiological parameter or physiological parameter into a mathematical parameter. Okay, and then we identify the biophysical relationships that must describe the temporal evolution of the variables. And then we should identify constraints and or assumptions. There may be constraints we should include. There may be constraints we should ignore. Okay, in this case, you can see, well, we include more and more constraints in order for our model to sort of represent the reality. Okay, so we identify constraints and or assumptions that must steer the definition of the model. And then we also examine the equilibrium point. So model equilibrium are useful to predict the steady state behavior of a physiological system. So you can examine the equilibrium without actually solving the differential equation because you assume all the derivatives to be zero. That is sort of the definition of equilibrium, means since does not change. This is also called steady state. So that concludes this presentation.